Welcome back. Now, let me remind you that last time what we have discussed is in the analysis of automated flow lines, that the performance can be analyzed based on the average production rate, the line efficiency and the cost per item produced. So, separately we have seen that how the average production rate could be found out, line efficiency can be found out and the cost per item produced on the line can be found out. So, we said, I will once again repeat and I will like to remind you that this is the TC. If you look at the diagram that we have last time drawn, that this is the ideal cycle time and this ideal cycle time includes the processing time and the transfer time, transfer that is required for the parts or the sub assemblies for going from one station to another station, one workplace to another workplace. Now, this TC is given for the longest workstation, as I said. That means, for the station which needs the longest time for processing, either it is once again assembling or the processing. So, therefore, for those machines which will take less time than the longest processing machine time, so that will have some sort of idle time. IDLE, idle time. That means, it has to wait for the longest workstation to complete the job and then do the operation, next operation. Now, this cycle time, as I said, I am just reminding you that this is the ideal cycle time and this happens if nothing happens in the line. That means, there is no breakdown happens in the line, all right, and 1 upon TC will be the ideal production rate. This is the maximum production rate that we can get. But in practice, since we have the flow line, automated flow line, which will consist of several automatic machines, there something or other happens, that is the machine breakdown, and because of that some time is elapsed for looking into that, for repairing and to rerun the machine. So, therefore, this is the time which we have to consider in the TC, so that we get the actual average production time, what we actually get, not the maximum one. This TP, therefore, that is that actual average production time will be more than the ideal cycle time by the F into TD we said, which is TD is the time taken for average downtime to diagnose the problem and make repairs when a breakdown occurs. Let me tell you that this TD actually much more than the TC. Okay. For example, if a processing time is about 10 seconds, so the TD can be 5 minutes or 10 minutes depending on the type of the downtime. So, what we are taking is that the average downtime, it is not the maximum one, on an average how much downtime is for the line. F we said is the frequency with which the line stops per cycle. If it is 1 in 100 cycles, it is 0.01 and so on. So, therefore, the mean time per cycle the machine will be down will be TD into F, and that TD into F we are considering here and adding up with the TC to find out actually the average production time. Average production time therefore becomes TC plus TD into F, and since we know the average production time, 1 upon time will be the production rate. So, the average production rate will be 1 upon TP, and in here all these factors will be known. So, therefore, very accurately we can find out what will be the actual average production rate in the line. Okay. By the way, coming back, I will just like to remind you that I said in one of my lectures saying that the time taken for duration of the time, okay, after you take the order from the customer and the delivery, this is reduced in case of the automatic automation, in case of overall manufacturing automation. This is simply because of the fact that we will be knowing very well and very accurately what will be the average production rate. Okay. So, everything is known. So, we can say that if I am taking that order today, I will be knowing that how much time it will take for me to deliver, and this is the time that we can maintain. All right. Okay. So, therefore, since we know the theoretical production rate, which will be 1 upon Tc, we can find out what is the line efficiency. That means, how efficiently the line is running, how much for how much time of overall operation of the line is operating, and for how much time the line is down. This is the proportion of downtime. So, therefore, E plus D, as I said, that you can check that this is equal to 1. This I will just reminded you. Then we discussed the cost per item produced, and we said that the material cost, then the line is the cost per minute to operate the line, and the cost of any disposable tooling is to be considered, and this will be the cost per workpiece. Then we started discussing the partial automation, and we said that these are the two reasons that it cannot be done overnight. So, therefore, mechanization of a manually operated flow line is often introduced gradually, and some manual operations are very difficult to automate, and if we even do that, it will be very expensive. So, there would be some manual operations, and therefore, the line cost will consider these factors, that how many number of manual machines you have and how many numbers you have the automatic machines. Okay. So, the average production time will be accordingly Tc plus Td into F, that is for the like in the earlier process, and here it will be F is the Td into F is given by the Na into P into Td. Small p is the probability of the line breakdown or jamming the parts. This we have discussed. Okay. Production and throughput, we said that the throughput time and the production time are different. Production time is the whenever one indexing happens, there is one machine coming out, one complete product coming out, and that is the production time. And throughput time is when what is the time that is taken from the beginning to the end for an assembly. Okay. So, therefore, throughput time is more than that, more than the production time. Let us take an example. Suppose we have a 8 station dial indexing automatic assembly machine, and this is driven by a Geneva mechanism with a driver rotational speed of 30 rpm. Find the production and the throughput time of the machine. I would like to remind you that when we have seen the Geneva mechanism, what is the driver rotational speed is the one which is rotating the pin continuously, okay, and that is the driver rotational speed. So, here we are taking that example of a 8 station dial indexing automatic machine, meaning that it will index and it will dwell for some times, okay. And it is driven by a Geneva mechanism. So, that driver mechanism is rotating the pin at 30 revolution per minute. This is the example. Every revolution of the driver constitutes one indexing of the assembly machine. You remember I said 10 seconds per car for the Ford. So, therefore, if it is rotating at 30 revolution per minute, that means the production rate will be 30 units per minute, because each time it is indexing, there is one assembly or one product which is coming out. Here it is that assembly machine, therefore, one complete assembly will be coming out in one indexing. So, therefore, it will be in 1 minute it will be 30 units, directly you can find out by knowing the driver rotational speed of the Geneva mechanism. Once we know that, production time will be 1 divided by 1 upon production rate, and therefore, production rate is 30 units per minute. So, therefore, it will be 1 upon 30 units per minute, and if you want to calculate for seconds, so into 60, that will be 2 seconds per unit. So, this will be the production time. Okay. What is the throughput time? Throughput time will be number of stations into the production time, okay. Because as you understand, we said that throughput time is the time taken for a complete assembly to be completed. Now, in case of production time, the number of machines is immaterial. I will once again repeat that. If in the line there are 100 machines or 100 or 1000 machines, does not matter, still in one indexing one complete part or one complete assembly can be taken. Now, in the throughput time, since it is the complete assembly time, so it depends on the machine. Okay. So, if there are more number of machines, it will take more time, throughput time. So, therefore, the production time into the number of stations will be equal to the throughput time. So, as you can see that if the production time is 2 seconds per unit, the throughput time is 16 seconds. It is obvious. Now, here if you have seen that we have not considered the line breakdown, and we said that in ideal case this is the thing, that if no breakdown occurs, then we will have the throughput time as 16 seconds and we will have the production time as 2 seconds per unit. Suppose there is a breakdown, okay. An 8 station rotary indexing assembly machine driven by a Geneva mechanism again has an indexing time of 3 seconds. We will change that example a little bit considering the machine breakdown. Under ideal condition, the machine produces a complete assembly in 8 seconds, achieving a production rate of 1 by 8 into 60 into 60, which is 450 per hour. Suppose each station malfunctions once in every 100 cycles. Let us assume one or more station malfunction will immediately jam the indexing machine, requiring an operator to make adjustment to restart the machine. Suppose that adjustment time and the restarting takes about 10 minutes, okay. That is the TD, all right. So, once again I will come back to that. This TD, so this is the TD, which is the average downtime to diagnose the problem. So, let us say in this example we have the TD is equal to 10 minutes, okay. That is when the line breakdown occurs, the 10 minutes will be taken by an operator to diagnose and to repair that fault and to rerun the line, okay. Now, let us see how this 16 seconds for throughput time and 2 seconds per unit as the production time changes only because of one breakdown per 100 cycles, okay. And there are 8 stations. So, this is the second example. All right. If the chance of a station malfunction is 1 in 100 cycles, the chance that a given station will not malfunction in a given cycle is 99%, because 1 in 100 cycles it is, or the probability is 0.99. One station malfunctioning does not mean that all other machines will work. So, this probability stands valid that all 8 stations must operate without malfunction to produce a completed assembly successfully. So, the probability of no malfunction in a given cycle is the product of chances of no malfunction at each station during that cycle. So, there are 8 stations and no malfunctioning probability is 0.99. So, therefore, this is the probability of no malfunctioning in a given cycle will be 0.99 to the power 8 to the power number of stations, which is 0.9227. What does it mean that 0.9227? That means out of 10,000 machine cycles, 9,227 assemblies will be produced. Is it clear? Once again I will repeat, it is 1 in 100 cycles the machine malfunction, okay, station malfunction. So, the station will not malfunction, that probability is 0.99 or 99%, okay. So, all 8 machines should work. So, therefore, 0.99 to the power 8 is this is the probability. So, therefore, out of 10,000 machine cycles, 9,227 cycles will work. That means, these many assemblies will be produced, 9,227 without malfunction, okay. And this cycle time is 8 seconds per assembly, let us consider, and this will consume then 9,227 assemblies, each one will take 8 seconds. So, this will be 20.5 hours or 73,816 seconds. So, this is the time taken for assembly if one machine or one workstation malfunctions in 100 cycles. Now, what about other cycles? In 10,000 there are 9,227 assemblies are produced, and 773 cycles at least one station will malfunction. So, that requires 10 minutes to repair. So, there are 773 cycles of malfunctioning, each requiring 10 minutes. per breakdown. So, it will be 773 into 10. So, this will be 7730 minutes, that is 182.83 hours of the breakdown. I would like to once again point out that 20.5 hours it takes to process the parts or to make the parts, whereas if even one breakdown happens, okay, in 100 cycles, it takes 128.83 hours. This is the real practical example. Okay. So, therefore, the total time to produce 9227 assemblies will be, we have 20.5 hours and we have 128.83 hours. So, this is total is 149.33 hours. Out of that, most of the time is taken has gone by the downtime. That means, when the machine is down and we have to repair, we have to rerun the machine. So, that means the percentage of downtime will be 128.83 hours divided by the total, which is 149.33. This is the one, okay. And this will be 86.3% of the total production time, that the percentage downtime we are having. That means, 86.3% is the machine is down. Just imagine we are talking about the one breakdown per 100 cycles. Okay. The production rate has been reduced from the total of 450 units per hour. Why you are talking about 450 units? We have already said that. Okay. That means, we have the here we have the 450 units per hour. This is the ideal one. Okay. If machine breakdown did not happen, then we would have produced 450 units per hour. Instead of that, what we are having is that we have 9227, this is produced in 149.33 hours, and this is taken 61.8 units per hour. So, just compare that we could produce ideally without breakdown 450 units per hour, and now we are producing 61.8 units per hour only because of the one station breakdown in 100 cycles. So, therefore, the efficiency of the assembly machine would be the ratio of the actual production rate to the real production rate, and that can be calculated as 61.8 divided by actually 450 units per hour. So, this is 13.7% of efficiency. Just imagine that 86.3% drop in the efficiency of only one station malfunction. Okay. 86.3% drop, because the 13.7% is only the efficiency, meaning that only 13.7% of the total production time the machine is working, that is the efficiency, that is what the efficiency means. Let us go further about, let us talk about the component quality. Why this breakdown occurs? Machine breakdown basically occurs if a component, faulty component comes to the machine and this gets stuck. That means, suppose you are assembling an assembly, and in that assembly one component goes in which is defective component. That means, the component, let us say dimensions are not well, not proper, or the tolerances are not proper. So, the machine does not know, it will try to fit in, but it will not go, then the machine stops. Once the machine stops, then the subsequent or the adjoining machines, since they are integrated, they also will suffer, they have to stop. We will discuss that in details later, but the predominant cause of assembly station malfunction is some random variation in the components being assembled. That random variation is basically the quality of the parts. Okay. Because the part is of inferior quality, it actually goes in and it makes a defective assembly, it stops the machine. Okay. Suppose in the previous example 90% of the assembly malfunctions were due to faulty components, and the faulty components I told that these here the tolerances may be wrong, or the length or the diameter is not proper, and so on. Elimination of the component quality problem would reduce the station malfunction rate, let us say from 1 out of 100 cycles to say 1 out of 10,000 cycles. Suppose in ideal condition, that means condition is such that we have improved the product quality. product quality in the sense the parts quality, which will go to the assembly. Okay. Quality has been enhanced, and because of the higher quality of the parts which will be assembled, now the machine breakdown will be less. And let us suppose that earlier we had in the other our earlier example, we have 1 out of 100 cycles breakdown. Now it will have 1 out of 10,000 cycles breakdown. Let us refigure the production rate and the percentage of downtime because of that. Now, probability of no malfunction in a given cycle, given typical cycle, this will be 0.999, because 10,000 cycle 1 out of 10,000 cycles it is malfunctioning. So, 10,000 minus 1, which is 999, it will function. So, it will function, that means it will no malfunction, it will be 0.999, and all the 8 machines have to be in the non malfunctioning position. So, 0.999 to the power 8 will be 0.9970, and this means that out of 10,000 parts or 10,000 machine cycles, 9970 assemblies will be produced without any malfunction, because the line is up for those many cycles. Okay. And cycle time is 8 seconds per completed assembly. So, it will take 9970 assemblies into 8 seconds, this is 22.16 hours. So, if we have, once again, if we have one malfunction in 10,000 cycles, because we have improved the quality of the parts, we will now have 22.16 processing time. What happens with the other? In other, 10,000 minus 9970, okay, this is 30 cycles, at least one station will malfunction, and that will require 10 minutes of repair time. This will consume 30 into 10, which is 300 minutes, that is 5 hours. 5 hours will be the downtime. That means, it will take 5 hours to take care of the downtime, to rerun the machine, to diagnose the problem, and so on. So, the total time required will be, we have 22.16 hours plus we have 5 hours. So, this will be 27.16 hours, it is the total time required. So, therefore, the percentage downtime we can find out that we have the 5 hours divided by 27.6 hours, 16 hours, and this will be 18.4%. The percentage downtime we had earlier, I would like to remind you, when we had the one breakdown per 100 cycles was 86.3. Okay. And here the downtime is much less, and it has become 18.4 because we have improved the product quality. All right. Now, the production rate will be, we have the 9970 units that we are producing, okay, for a total of 27.16 hours. So, this will give you 367 units per hour, and therefore, the efficiency is, earlier ideal one I have shown it to you, it was 450 ideally. If breakdown occurs in one breakdown in 10,000 cycles, it will be 367. So, therefore, the efficiency is 81.6%, that is 367 divided by ideal 450. So, this will give you 81.6% efficiency. Efficiency has grown up much more. Okay. All right. So, here what we are saying is that the improvement in the product quality is actually bringing down the downtime. That means, the machine efficiency is going up, the machine breakdown will be less. What is the consequence? We cannot really improve the product quality just to get this, because while improving the product quality, we are also investing money in that. Okay. And those details we will discuss in the later stage, but you have to understand that although we are getting the production efficiency much higher by improving the product quality, which are assembled, it is not that easy, it has to be properly justified, it has to be weighted, and then taking the decision that how much improvement in the product quality you can get, so that overall you can get the cost per piece ideal or lower. Next item that next topic that we will be discussing is the feeder, the small engineering parts which go into the assembly for the assembly process, and the feeders which are used for feeding those small engineering parts to the workstation for assembling. One of the most popular, one of the most important and the most used feeder is the vibratory bowl feeder. As you can see the diagram here. In this, here is the 3-dimensional picture shown, pictorial view given. So, in here we have the bowl feeder overall. This is the bowl, okay, and here you have that outlet. The bowl is closed here. Okay. Inside the bowl there is a track along the outer wall of this bowl. The entire bowl is supported by the suspension springs to the base of the bowl feeder, okay. And on the base there is an electromagnet. So, that electromagnet actually imparts the vibration to the bowl and anything that is located in the bowl. Now, the small engineering parts will be located at the base of the bowl, and as the electromagnet imparts the vibration causes the parts to ride along the track of the vibratory bowl feeder and finally come out of this feeder. So, this is the outlet. Now, how it happens and why it happens? Vibration is applied to the bowl from the electromagnet mounted on the base. Here is the electromagnet. It has a torsional vibration about its vertical axis coupled with a linear vertical vibration. So, what it does is that this electromagnet, it actually produces a vibration like this, okay, vertically, and a vibration like this, okay, that is a torque. It has a torsional vibration, this is the torsional vibration about its vertical axis coupled with a linear vertical vibration. This is the linear vertical vibration, and there is a torsional vibration. So, because of that, as a result, the small parts which are located at the base will be forced to ride along the track of the bowl feeder, and it will come out of the exit. So, the details analysis and how to design the vibratory bowl feeder we will discuss in the next class. Thank you very much.